To discuss a little bit more on the hardware of scanning electron microscopy, the first component that came in our mind is the electron gun. Normally, the electron gun is comprised of electrode in the cascaded in the system, which is referred to as Wagner cylinder. So in Wagner cylinder, the electrode is mounted, and this electrode is of different materials and shape and sizes. The very common is the tungsten filament. The tungsten filament can also be viewed in the classical lamps that in our household. So in classical lamps or bulb, we refer to as inside this bulb or lamp there is a filament made of tungsten which glows. So in case of scanning electron microscopy, a very specialized tungsten filament is mounted, and this tungsten filament is in of V shape. So it either can be a V-shaped tungsten filament, or it can be of LAB6 material electrode, the pointed tip electrode, or the field emission gun, very specific and very specialized gun, is a pointed tip gun. A pointed tip gun is very much different from the LAB6, which is also a pointed gun. But in case of field emission gun, the characterization and the material composition of field emission gun is totally different from this LAB6. But these three different type of materials are used inside the electron gun. This doesn't mean that these, for example, if tungsten filament is mounted inside the electron gun, then it can be replaced with the LAB6 or FEG field emission gun. No, these tungsten element, the gun is made of this gun mounted with the field, tungsten filament is of different gun. LAB6 can be used in different guns, and FEG can be used in different electron gun. So these three are not interchangeable. These three refer to as three different guns. So what is happening here, if you supply the electricity, then what is happening, the electrons are emitted from the tip of these guns or these filaments. So, and then these filaments, when they emit electrons, they protruded from the Wagner cylinder, and they are deflected or converted by the electromagnetic coils, which can be referred to as condenser lens and objective lens. In a simple view, you can see that there are two tips, and on these two tips, this W filament of the tungsten filament is mounted. So this tungsten filament is very teeny and small. It cannot be visualized in this or difficult to visualize in this this image, but on these two tips this tungsten filament is mounted. Similarly, the electron guns, there will be some different electron guns where LAB6 or FEG are mounted, but the purpose is very much same. Because of these guns, the high energy electron beam is generated. Second came the lens. The electromagnetic lens made up of a coil of wires. So these coil of wires, when they supplied by the electricity, then they deflect the electrons which are passed by or passed through. So because these electromagnetic lens, they are on the path of they are mounted on the path of electron gun with a very specific purpose. So these electromagnetic lenses are referred to as either condenser lenses or objective lens. Both these condenser lens and objective lens have different function, can be discussed in the later slides. So there are two things that are very much important for us. one is the spot size and the other is the focus. As I earlier mentioned in the slides, that the spot size usually refer to the scheme that how fine you want to view the image, or how fine you are scanning the surface of specimen. If the scanning is very much fine, then you have to use small spot size. If you are just want to see the image, the rough image or the coarse image very quickly, then you have to use a large spot size. So normally the condenser lens it controls the spot size, whereas the objective lens it controls the focus of beam. So in case of condenser lens, how it controls the spot size. So if the convergence of beam is low, then the spot size will be large. If the convergence of beam is high, then the spot size will be small. So this small spot size or large spot size are relative with respect to this convergence. So low convergence or high convergence. Low convergence means the convergence is away from the condenser lens. So here's the condenser, gun, aperture, condenser lens, again the basic aperture. This aperture is from the Warnet cylinder, and this is aperture that you normally use in the scanning electron microscopy, and again the objective lens and then the sample. If the convergence after the condenser lens is away from the condenser lens, then it normally refers to the large spot size. If this convergence is very much close to this condenser lens, then it refers to as high convergence and the spot size will be small. Similarly, the objective lens it controls the focus of beam and the focus of image as well. So focus of beam or focus of image, they are the same thing. So once you get the convergence by the condenser lens which control the spot size larger or smaller, then the objective lens it tries to focus the beam of electron on the specimen. So by focus means if the target beam is on the exact spots you want to view it in the scanning electron microscopy, then it's called focus image or all focus. If the focus, if the beam is converted or converged at the very close to the objective lens, the image is out of focus or it's called over focus. If this conversion is far away from this objective lens, even far away from the specimen, then it's called under focus. Under focus or over focus are not required. You will always see the good image if it is at focus. So objective lens it control the focus of image, and the condenser lens it control the spot size. So you have to remember these terminologies, that condenser lens normally control the spot size and objective lens normally control the focus of beam or focus of image. Aperture is the mechanical element in scanning electron microscopy. Basically, it's a metal strip which has various size through holes, and it is just placed just above the objective lens, and it serves very important function because the electron gun generates high energy electron. It passes by the condenser lens. As you know, the condenser lens has a function to control the spot size, the larger or the smaller spot size. Once this spot size is controlled, then the electron beam is passing by this mechanical aperture. what is actually happening after condenser lens, that some of the electrons, they get off axis or they loses some of the energy, because during a path from the electron gun toward the sample surface, electrons are continuously getting off axis or they are losing energy. If these electrons, the off energy or off axis electron, if they reach to the sample, then we will have not much control over the electron beam, because these off axis electron will create artifact. Because as you know, there are two types of detectors who form the image. One is the backscattered detector, the other one is the secondary electron detector. So backscattered electron detector or secondary electron detector, basically they form the image. And if these off axis electron, if they reach to the sample, they will be not focused, they can target any other area of the sample. And if these electron, the off axis electron, if they hit the surface, either they will be backscattered or they will impart some of the energy to the outermost shell of the atom of the surface of the specimen, and they create secondary electron. And if these both the electron, the backscattered electron or the secondary electron of this off axis electron, if they reach to the sensor, then the image formation will be blurred, or you will not get the image of the particular small teeny surface. So to get rid of this off axis electron, you need something which can either absorb or which can retain this off axis electron, so that these off axis electron shall not pass by the objective lens toward this sample. So this to control this off axis electron, we will need this mechanical strip with various size holes, just to control the off axis of off energy electrons that are passing by and reaching to the sample via this objective lens, which has a function to focus the electron beam or focus the image. Very much similar to the magnification, focus and spot size, we are using another terminology named as accelerating voltage. So to acquire a good image from a scanning electron microscopy, normally we see or we say that increase the accelerating voltage or decrease the accelerating voltage. So what will happen if we increase the accelerating voltage of beam? By increasing the accelerating voltage, we are getting higher energy electrons, and by these high energy electrons, the advantage will be we will have a higher signal in the final image, or this higher signal means we will have a lower noise final image. The final image will be of higher quality, good quality by this low noise or higher signal. Secondly, if the high energy electron they reaches to the sample, they can penetrate to the greater depths. The third advantage of this increasing accelerating voltage is that we can acquire the brighter images. However, this accelerating voltage is not always beneficial. It has some disadvantages as well. By increasing the accelerating voltage, we are reducing the structure details of specimen surface in case of secondary electron mode. As you know, most of the image that acquired by scanning electron microscopy that are reported in the literature are by the secondary electron mode. So by increasing accelerating voltage, we are compromising the fine quality image of secondary electron mode, because we are reducing the structure details of specimen surface. Why this is happening? Because the high energy electron, they can penetrate to the greater depths. If they can penetrate to the greater depths, then there is a compromise on getting acquire the secondary electron from the surface of the specimen. Secondly, if we increase the accelerating voltage, then there is increased electron built up in the insulating samples. So if the electrons they are built up on the insulating samples, then they are causing charging, and ultimately this charging will help to produce artifacts. Third disadvantage of accelerating voltage is that by increasing accelerating voltage, we are increasing the energy of electrons. So if they hit the surface, then more heating or more heat energy will be generated by collision of this electron towards the nucleus of atom. So by increasing this heating or heat energy, the surface or the sample will be definitely get damaged. The fourth disadvantage of this increasing accelerating voltage is that the number of backscattered electron will definitely increase, because as you can imagine that high energy electron will definitely increase to the greater depth of the sample, then more backscattered electron will be generated, and maybe this increase in backscattered electrons, the backscattered electron may reach to the secondary electron detector. So if the chances of this backscattered electron reaching to the secondary electron detector is increased, then the resolution that you are getting from the secondary electron image will be blur, or you're compromising the secondary electron image formation. So it's very wise to control the accelerating voltage into the optimal limit, and this optimal limit varies from sample to sample. To show the effect of increasing the accelerating voltage on material is depicted here. So there are two types of specimen we have: a low atomic mass number and the high atomic number. If the sample has low atomic number, means the atoms will have a smaller nucleus. If the specimen is comprised of high atomic number atoms, then these atoms will have a relatively bigger nucleus as compared to the low atomic number specimen. So what will happen? The electron beam of a normal accelerating voltage, they penetrate to the greater depth in case of low atomic number specimen as compared to the high atomic number specimen. So depth of penetration will definitely, in case of low atomic mass number specimen, will be more as compared to the high atomic mass number, because the nucleus of low atomic mass number atoms are much smaller as compared to the high atomic mass number. However, if we increase the accelerating voltage, then the depth of penetration will be much larger in case of low atomic mass number, and similarly the depth of penetration will also increase in case of high atomic mass number as well, because you are increasing the accelerating voltage. If we sum up both the things here in the diagram, then you can easily see by increasing accelerating voltage, the depth of penetration will increase in low atomic mass number as well as high atomic mass number. So to sum up the discussion, we can easily visualize the impact of increasing accelerating voltage on the material or specimen, because by increasing the energy, by increasing the straightening voltage, we are increasing the energy, and by this increase in energy the electron beam can penetrate to the greater depth, both in case of low atomic mass number and high atomic mass number. Definitely there the penetration in case of low atomic mass number specimen will be much more as compared to the high atomic mass numbers. That's the end of lecture. If you have any question, then you are please feel free to ask it with either the WhatsApp group or in the Google Classroom. Thank you for paying attention.